So the next definition in Article 100 is ground fault circuit interrupter. Now, this video covers the definition. If you want to know where GFCIs are required, that's a different discussion. Go to section 210.8 and 422.5 and a few other sections back in chapters 5 through 8. You know, if you're looking for swimming pools, go to Article 680. This just covers the definition. So what is a GFCI? Well, it's a device that provides protection for people by de-energizing the circuit when a ground fault exceeding the value of a Class A device occurs. Okay, so from left to right, we've got a GFCI circuit breaker, as we know. Here in the center, we have probably the most common type, a GFCI receptacle. And then over here, we have integral GFCI to the attachment plug of this hairdryer. So those are all three different examples of GFCIs. Now, it's important to note a few things in the definition. First of all, when we talk about GFCI protection, we're talking about protecting people, all right? And we're talking about Class A devices. So a Class A device, we're going to find out here in just 1 second what that means. But suffice it to say that if the code requires GFCI protection, it has to be a Class A device, right? Because that's the definition. The only type of GFCI that meets the definition of a GFCI is a Class A GFCI. So sometimes I'll have questions from people, and they'll say, Ryan, I've got a commercial kitchen. Do I have to have GFCI protection for the receptacles? Can I put in GFPE for the receptacles? And the answer is no. If the code requires GFCI, it has to be Class A because that's what the definition says. Class A is intended to protect people. So what is a Class A device? It's talked about in the informational note, and they kind of cleaned up some language in the 2020 NEC as well. But a Class A GFCI device opens when the ground fault current exceeds 6 milliamps, and it does not open if the ground fault current is less than 4. So somewhere between 4 and 6 milliamps of ground fault current or leakage current. That's where a GFCI opens. So what am I trying to show here on the photograph? Well, the way a GFCI works is it monitors the current between the circuit conductors. And that's true whether it's a 120 volt circuit or a 240 volt circuit or a three-phase circuit. It doesn't matter. It measures the difference in current between the circuit conductors. So what do I mean by the circuit conductors? The ungrounded conductors and the grounded or neutral conductor if the circuit uses one. So here on my saw, I've pulled the trigger and I'm measuring the current around the entire cord. Now, if I have current, right, we have to kind of go back to Kirchhoff's law. Current leaving the power source must equal current returning to the power source. If 10 amps leaves the source, 10 amps has to return to the source. That's not my opinion. That is a fact, right? So the idea here is we want the current to return to the source on the intended path. If it goes out on the hot, we want it to come back on the neutral. Or if it's a 240 volt circuit or a 208 volt single phase circuit, if it goes out on phase A, we want it to come back on phase B, right? So what I'm showing here is I have clamped my ammeter around this 2-wire cord. I pull the trigger, 10 amps goes out on the hot, 10 amps comes back on the neutral, so it results in a net zero effect if I'm measuring the current across both. If I had a ground fault, let's say inside this saw, we had like a frayed cord or something on the internal components. So the cord energizes the metal parts of the saw. And I put my hand on my metal table and I pull the trigger and I get shocked. Well, the motor itself still pulls 10 amps. So 10 amps is coming out, 10 amps is going back on the neutral. But some current is going to be going through me, right? Because I'm getting shocked because of the ground fault. So it's actually not 10 amps leaving the power source, it's 10 plus a few milliamps. Let's say it's 10 amps plus 10 milliamps, so 10.01 amps. That 0.01 amps is flowing through me. It's not going back on the neutral. So if I still had my ammeter connected, I would actually read 0.1 amps, right? Because there's more on the hot than there is on the neutral. Well, that's indicative of a problem. So a GFCI works in that exact same way. GFCI is measuring the current on the circuit conductors, and they better equal the same thing. Current leaving must equal current returning, right? So we're going to measure it on the intended path, and as long as those numbers are net zero, then everything is working correctly. But if all of a sudden I have more current on one hot than I do on the other, or if I have more current on the hot than I do on the neutral, that means current is going somewhere that we don't want it to go, and we're going to open the circuit protector device. And that's why you don't need a neutral for a GFCI to work on a line-to-line load, right? So if I had an air conditioner that I needed a GFCI protect, for example, do I have to have a neutral? No. I can just take my two conductors, and if the air conditioner pulls 23 amps, that means 23 amps on the black, 23 amps on the red. The GFCI measures between those. It equals zero under normal conditions, so it doesn't open. If one of those two conductors started pulling more current than the other, well then that means that current's return path is going somewhere unintended, and it's going to open the GFCI. Why does it go when we exceed 6 milliamps? And why do we want to make sure it doesn't trip when it's less than 4? Well, because less than 4 milliamps really isn't going to kill anybody. More than 6 milliamps could result in a painful shock. How do we know this? Well, Dr. Charles DeLisle is the inventor of the GFCI. I don't want to say he invented it. The concept was around actually before Dr. DeLisle, but he patented it. He really figured out where it should open. We had protective devices going back to like the 1930s, but we didn't know where they should trip. So we came up with a concept of like a GFCI, but it tripped at 1 amp of leakage current. Well, 1 amp, you're deader than dead if you have 1 amp flowing through you. So that doesn't protect anything. Dr. Charles DeLisle did research and actually figured out where the device should open. And then he patented his Class A and Class B GFCI protection devices. So 4 to 6 milliamps. According to Dr. DeLisle's research, a not painful shock is about 1.8 milliamps, and a painful shock is about 9 milliamps. Now, these are based on averages for men and not women, although the numbers here are for women as well. So that's how he figured out where a GFCI should trip. Somewhere after you can feel it, but before it becomes really painful and dangerous. Now, how did he know that these were the numbers? Well, Dr. DeLisle was a professor of electrical engineering for University of California, Berkeley, and he published a document called The Effects of Electric Shock on Man in 1956, if I'm not mistaken. And that paper, which you can download for free, and it's worth checking out, that paper was based on his research. You see, back in the 40s and 50s, we didn't have all of these things like oversight committees or ethics committees or consent, or certainly informed consent. And if you were in Dr. DeLisle's graduate class as an electrical engineer, if you wanted to get some extra credit, you could volunteer to help him with his research. And I use that term volunteer pretty loosely. I think if you wanted to pass the class, you were probably going to volunteer whether you wanted to or not. So here's one of Dr. DeLisle's volunteers or victims, however you want to say it. We got one wire in his left hand, the other wire in his right hand. This guy back here is turning on the electricity, and basically Dr. DeLisle was measuring the current and figuring out what it did to the volunteer. You know, how bad did this hurt? So those are my dogs in the background. Thanks for that. Here's Dr. DeLisle back here administering the test. Here is the volunteer. This guy back here is writing down the test results, and this guy here, who seems to be enjoying this far too much, his job is to hold the guy's hand down and make sure he doesn't let go. So we want the GFCI to trip somewhere between the not painful and painful, somewhere between this point and, you know, this guy here experiencing the non-painful and this guy experiencing the painful. So there you go. That is a GFCI. We also have ground fault protection of equipment. Now, GFCI protection is for personnel, for humans. GFPE is for equipment. So ground fault protection of equipment. That is a system that protects equipment against damage from ground faults by opening the circuit device at current levels lower than the circuit's overcurrent device. Okay, so here in the photograph, we have a 20 amp circuit breaker, and if you can see the panel schedule, it says it's for the heat tape. Now, I live in Salt Lake City, Utah. Heat tape is a pretty common sight here. So if you've got a lot of snow on your roof and you want to melt the snow to prevent ice damming or damage, then you would install a heat tape system. And the heat tape melts the snow, and there you go. Now, a heat tape system actually relies on some amount of leakage current. That's how it does its job. So it is outdoor equipment. You don't want to put on a GFCI because a GFCI might actually trip the heat tape circuit because the heat tape actually works by having a small ground fault. But you also want to make sure it's not going to burn the building down. So you install a different level of protection. We call it equipment level protection, ground fault protection of equipment, GFPE. Now, here's the big misconception when it comes to GFPE. What current level does that device trip at? Some of you might jump out and say 30 milliamps, and you might be right, but you might also be wrong. The fact of the matter is there's not a standard. A lot of manufacturers have kind of shaken hands and said, look, at the small, molded case circuit breaker level, we're going to just kind of agree that we should trip at about 30 milliamps. But the product standard does not give a value. And when you get into bigger systems, and by bigger systems, I mean three-phase, solidly grounded, Y-connected, 277, 480 volt systems, once you get into those systems and you have a 1,000 amp or greater overcurrent device, that main has to have ground fault protection. And it certainly is not set at 30 milliamps. It's set at like 1,000 amps, or it can be set significantly higher than 30 milliamps. So don't think that that's a standard. Ground fault protection of equipment does not protect people. It protects equipment. You cannot use ground fault protection of equipment as a substitute for GFCI. So where do you need ground fault protection of equipment? Off the top of my head, you have 426.27 for heat tape, and you also have 427.27, which is for what do you call it, like pipe trace heating, which is kind of similar in concept to heat tape. And then you've also got it for services and large breakers in 230.95, 240.15 as well, if I'm not mistaken. If it's not a service and it's a feeder, that's where you would look for the requirements for it. Be sure to like, follow, subscribe, and ring the bell.